All right. It's 5 o'clock now, so I'll get cracking. Welcome to the next lecture in Unit 6. So if you remember, we still have a couple units to go after this, but they're in a relative size a little bit maybe smaller each than say this one. And yeah, we'll get onto that next week. But for the rest of this week, we'll be dealing with Unit 6. In particular, today we'll be covering a lot of content which is very, very relevant to Project 2. Okay, so today's the lecture to pay attention to for Project 2. If you haven't seen, Yoni actually has a beautiful recorded video that goes through the questions in Project 2 and explains what all the questions mean, what's the system about, and what kind of answers we want. And as if you watch that video, there's parts of that you could already do. There's parts of it that depend on Anna's lecture, Anna's perspective seminar next Tuesday, and there's parts of it which will depend primarily on the stuff we talk about today, actually, and a little bit tomorrow. So yeah. After that, I'll stay with you guys and do what we're calling Unit 7, which is all about data. So if you remember last Tuesday, the last lecture, we started talking, leading into this whole idea of simulations and Monte Carlo. So Monte Carlo was this idea of using randomness to figure out the answers to problems which, should have some deterministic answer, even if it's like an average or something, that's like a deterministic answer. And Monte Carlo is like usually a simulation or optimization technique you use on a computer using randomness. So last lecture, we really dove pretty deep into like how computers, which are sort of deterministic machines, how does a computer generate randomness? And we talked about random number generators with their sort of internal hidden state and different schemes of generating numbers. Once you've generated, say, a uniform random number, how do you sort of turn that into a certain distribution according to some probabilities, or like an exponential distribution or a Gaussian distribution or some other distribution using different techniques, okay? So all that was, because this is partly, it's a, math sort of course, and we sort of want to teach you how things work on the inside. But mostly during the course, you're going to be using random number generators that are built into Julia and be calling them using functions like rand, okay? But it's still important to know how it all works. So I skipped over this bit at the end about the Poisson distribution. I think I'll just continue skipping over that so we can focus on the discrete event simulator. If anyone has any questions before I proceed, write it in the chat or call out the room. Does anyone want to bring anything up before we get into the meat of the lecture? No, we're all good. Everyone's purring along happily with Project 2 then, I take it. Nice and easy peasy. Yeah. So yeah, if you have any questions at any point, just remember, just yell out, just write in the chat. There's really no problem to stop and to discuss something. So discrete event simulation. Okay, so we're going to talk about this. We're going to implement one of these in this lecture. We're going to, you can use some of the code in this lecture, copy and paste it into your project too. And you're going to kind of like enrich or whatever the simulator with the features you need to do your project, right? So that's the plan. So what is a discrete event simulation? Well, some simulations like fluid dynamics, for example, they're, if you want to look at how, say, a rocket flies through the air or something, they're usually modeled in terms of continuous things like pressure and flow and different things. And you might be solving like a partial differential equation or something like that in order to figure out, the dynamics of that system. Other systems, especially things which are more abstract mathematical models, and rather than like really very, very low level physics, things that are more abstract mathematical models things often happen in discrete events. So when we say an event, just remember it's something that happens at a single point in time, okay? So if you think of it like a moving object, it's at an infinitely different many points in space at infinitely many different points in time. But really, we're talking about events where it's sort of like it's here and then it's there. Now, I will give an example in physics where we have motion, and what's happening between the discrete events is the velocity staying constant, and the motion is very trivial in between. But we'll get to that. We'll get to that. That's fun. So what we have some events that happen at points in time. Now, time is a scalar quantity. We can order it, right? There's now, there's yesterday, there's tomorrow. And we all know that, tomorrow is going to happen after yesterday, right? So there's always going to be some ordering to the events in the system. And that also means we have a sort of causality in the system. Something that happens at an early point in time can affect things that happen later on, but not vice versa, right? So there's some notion of time, some notion of causality, and some ordering of events that happen. And these events are discrete. So there's going to be a finite or a countable set of events happening in your system, and we're going to be interested in that. So we have some, discrete countable number of events, first one, second event, third event, we can actually give them numbers if we wanted to, and so on. And so let's just talk about a really simple example first, just to give you, something concrete to get your hands on, and we'll talk about a few other examples before writing a more fancy simulator, okay? So let's just look at a call center, and this is one of those call centers some of us probably hate them, where they get a bunch of people in a room and they ask them to call people and make donations, okay? So, it's not that I don't like a good cause, but it can be distracting when you get randoms calling you, and most people probably block unknown numbers anyway. But so let's look at this system. Assume there's like 5 workers in this call center, and what they do is they ring people and talk to them, and depending on who they talk to them for different amounts of time, right? Some people are uninterested and they hang up straight away, and other people are on the line for a while discussing whatever philanthropy is going on. And in this model, we say that the duration of a call is exponentially distributed, right? And the mean duration of call is 7 minutes. So half the calls will be like less than 7 minutes and half will be longer. Well, that's the median, but is that the same for an exponential? I can't remember. I guess it'd be the half. Anyway. So assume that what we're going to assume is that short calls that take less than a minute and a half are people who don't want to donate, and longer calls than 1.5 minutes are people who will donate some amount of money. And the longer you stay on the phone line, just as a mathematical model, the more you're going to donate, right? If you're going to give more of your time, you're probably going to give more of your money. So for every minute you stay on the line, you donate $2.50. So we could simulate how this call center generates revenue as a function of time using randomness, using Monte Carlo simulation, okay? So it's not a very fancy or even particularly interesting example, but we just want to sort of get something down in code and on paper and in plots, so you can see what's going on, okay? So, just to learn how a simulation like this would work. So it's not meant to be super mind-bending mathematics here, but we'll get through this. So what we're going to do is we're going to create different realizations or trajectories. So in a given realization, you like if you're playing a game or something, a realization of the game is like you roll the dice and you get actual numbers, right? You roll the dice again, you get more numbers until the game's finished. And that would be like one realization or one random trajectory, one Monte Carlo trajectory, sometimes even one stochastic trajectory if you're doing these more continuous things. And we have an ensemble of possible futures, some kind of, with some probability distribution or continuous probability distribution over all possible realizations or trajectories in the future, right? So some possibilities, you ring up 1,000 people and they all say no, for example, that's possible, but it might have a low probability, right? And other things, more typical situations will have a higher probability in this space over probability over space of all trajectories. So we're going to use Monte Carlo to actually sample those space of trajectories and generate 3 trajectories. Okay, so there's going to be a loop here, or not a loop, but we're just going to call this function 3 times at the bottom. So we'll just bring in some basic, the plots package, the random built-in library, and the distributions library. Okay. And we'll set the random seed so it's all kind of nice and repeatable, so that you can, be nice and scientific about this. And just some basic definitions at the top. The call duration is a function, it's random. So it's not random, remember it's pseudo-random, it depends on the hidden state that's hidden inside this random number generator here that this is referring to, okay? So it's a function, it will mutate this sort of seed and spit out a random number according to the exponential distribution. Exponential is something you get in distributions.jl, and then you can call rand on that once you construct it. So it's a nice way of building different samplers for different distributions. Money made, this function, this logic we said before, if it's less than 1.5 minutes, then no money's made. If it's more than that, it's $2.5 per minute. Okay. Then there's this main function, the actual simulate function, which is going to depend on these other functions. So we got 5 call workers, and the way we're going to model the system is we're going to keep track at every point in time for each of the 5 call workers. They're all on a call all the time, right? It's a call center. That's what people do. What we keep track of in this vector here, this current workers calls vector, is for each person we keep the time for when their current call is going to end. Okay, so we keep this vector of all the current calls, and when we begin the call, we're going to draw according to this distribution how long the call takes, and therefore we can predict, we know when the call started, we know how long the call is going to take, so we can figure out the time when it ends, okay? And that number of when it ends is going to go in this vector. So there's 5 operators with labels 1 to 5. We start at time equals 0 with no revenue. Why is there a copy there? Not sure why that copy's there. Anyway, and then we're going to do this loop. So we have this thing we call a log. So we're just literally recording every time there's an event, what's the state of the system, what's the time, and what's the revenue at the point in time that an event happens. Now, in between events, the revenue stays constant, right? The state of the system doesn't change in between events. Nothing in this vector here is changing between events, and the revenue isn't changing. The only thing that's sort of evolving, if you would, between events is the time itself. Everything else is sort of constant. And from these sort of logs of outputs, we're going to stitch it together and make a graph. That's the point of those. Okay. So we're going to loop forever until for some reason we call this break. Okay. So remember, break is the thing which gets out of a loop, and there's this while loop here. While true is just an idiomatic way of just looping forever. And then, but there is some way of getting out of it. It's not Groundhog Day. There's a way out. So we have this function called argmin. So this is find the index for which the value is minimal. So we have 5 people on calls, and we've figured out when they're going to end. So we're going to figure out which is the soonest call to end. And I here is the index of this array, which corresponds to the soonest ending call, right? And we can get the time from that index again. Basically, we're going to continue this loop until we've done 60 minutes, so an hour of calls. And so if we've sort of exceeded this limit of 60, we kind of like do a final log of the answers and then sort of break, right? If it's smaller than 60, we go down here, and we log these events. So we push the time on, and we add the revenue depending on money made, right? So that's a deterministic function of this thing. And we put that in the log, And finally, this is the interesting bit. We go back and we mutate that state that's keeping track of when the next call ends or how long the next call is. And like that. So that's how this sort of simulation works. And at the end, we spit out the vector of times and the vector of revenues. There's this little helper function here, which lets us stitch together these vectors in a way that the plot looks like a step plot. So I think there is actually like a step plotting mode or something we could have used instead, but this is just a more explicit way. Don't worry about the logic of that. It's just like making the graph kind of step up like you see here. And we do this 3 different times with 3 different colors. And we see there's 3 different curves down here, or trajectories or realizations of how much money we've made as a function of time, right? And so this is the kind of thing we're going to generate in this unit and in project 2, are these different trajectories or realizations of what's happening. Now, you could notice some things about this. These curves, they are different, but they have a similar kind of trend. They don't ever get too far apart. They're both trending up at a relatively constant rate, it's a pretty simple system that you'd expect to make so many dollars per minute with the system in a linear fashion. So that's what we're sort of observing. Okay. And what we can see is you can see like these flat regions. So in between these different points in time, everything is sort of static. So that's that discrete event that's coming into play, all right? Are there any questions? Oh, here we go. We got a question over here. I probably ignored it for ages, sorry. Will the argmin be replaced with a min heap? Yes, it will. So this is really just a very simplistic kind of model. There's a little comment here to say that, 5 is not a very big number, but like if there was a large number of call operators, you would actually spend all your time looking for the next one. Whereas we could use a special data structure to figure out what the next one is for us. So we don't have to do all that work all the time. And so we're going to build a simulation that has that kind of property. It's a bit faster and a bit more generic. So before we build that and talk about the kind of problems we see in project 2, I just wanted to mention some things you can do with these kind of simulators where it's discrete, right? So it's often used in things like logistics, social services, communication industries, so like, modeling phone calls and internet packets and things like that. Can model like epidemiological, I can't even say the word, that model like the spread of diseases like COVID and things like that, which is not a deterministic process, it's kind of random. So like a person might get COVID and then they might spread it to 1 person or 0 people or 5 people, or, those kind of models. And the one, I'm a physicist, so the one I really love playing with is this idea of a simulation of ideal gas. So I actually coded up something like this in OpenGL during my PhD instead of doing the work I was probably supposed to do. And you can kind of see here, this is a discrete event simulation written, I think, in JavaScript. And you can kind of see, this is a model where, there's actually kind of 2 types of events in this model. One is that 2 balls collide and their velocities change. And another event is, okay, we've finished rendering to the screen and we want to render the next frame. Okay, so when you want to render the next frame, you advance all the balls by their velocities, right? And when there's a collision, you kind of update just the status of the 2 balls that collided. And you use one of these min heaps that Mitten mentions to keep track of which of the next 2 balls to collide and stuff. And what you can do is you can kind of like put more things in, and you can put gases of different masses, so light ones and heavy ones. And you can kind of see at thermal equilibrium, the light things and the heavy things have the same amount of kinetic energy, which is half mv squared on average. And the lighter things have a smaller m and therefore a bigger v, a bigger velocity. So the red ones are bouncing around like crazy. We can turn up the heat and do sorts of things. We can add more stuff, so it's getting pretty full. Hook it, and then it kind of does something kind of interesting. It actually blows the lid off. And it's doing something here. The fast particles near the top are leaving, and the rest of the particles that stay are actually the ones with the smaller velocities, and it actually tends to cool down when it expands like that. So that's kind of cool. Right, just let that go. And then I should mention also the kind of work that I do. I'm at a startup called Alara AI, and we do event simulations of people's businesses, sort of repeatable processes, whether it's sales or production or something. And we use these kind of discrete event simulations with randomness and machine learning and various, integrations with customers' data sources. We try and figure out businesses' future and then try and optimize that for whatever they care about, whether it's throughput, profit, or some other business objective. Yeah. So this stuff, I think this is a really good component to put in this course, because it's this kind of thing. If you're an applied mathematician, you're out there. It's a technique that gets used in a lot of different places, so it's good to be aware of. Yeah. All right. So we're going to go a bit deeper into another simulation and code it up, and it's going to start getting a little bit more like the kind of examples in Project 2. So we've got a health clinic and a waiting room, okay? And so this is a bit of a queuing problem. People are queuing up to see the doctor, right? So they go into the, there's two doctors, right, in their own rooms, and there's a secretary, and there could be people waiting in the waiting room. There could be people seeing the secretary or the doctors, and they all have to kind of like, only one person can deal with the doctor at a time, only one person can deal with the secretary at a time, and so on. Okay, so when you come in or when you leave, you need some time to talk to the secretary, so you may have to queue like a second time, right, just to see the doctor, which is probably something we're all familiar with. So things we might want to track are like the number of people doing any of these activities. And also we want to think about the events that happen in this thing. So whenever you want to come up with a simulation, you want to think about what state do we keep at a given point in time? What do we know? And like the rest of history, we just forget, right? There's certain things we care about, and then the rest of history, we don't have infinite RAM on our computer. We want to forget things, maybe log some things in those logs that we showed before, and then forget the rest. So we have some state we want to keep track of to use to predict the future. We have events. So what things can happen that change that state, right? And with these two things, you can build an event simulator. And so we'll go through that process here. We'll see how these two things go into a very generic simulator at the end, which you could then start taking that generic simulator for your project to. So events that might happen in this: patients arrive at the clinic, the patient then goes to see the doctor in the doctor's room, patient leaves the doctor's room to speak with the secretary to pay, let's say, and the secretary might be on the phone or something, right? So so each of these events, again, it's a discrete event, right? Between the events, the state, this set of state doesn't change between the events. And then we've got an ordered list of events, ordered in time. And what they do is they change the state. And they may also, they do another interesting thing. They may also trigger more events to put in the queue. So if you let's say your simulation gets to a point where there's no events left, right, then nothing's going to change for the rest of eternity, right? So usually, like before, we have this pattern. When you evaluate one event, you tend to create another one or two or three, like more events afterwards, okay? And that's where it happens. And that's the trick, is that we don't want to keep all of history of every event in RAM all the time and work through that. We don't want to like pre-generate, like we want to just generate like that small amount of state that we need and walk forward and then log the statistics that we care about. Okay. So the question that the simulator needs to answer is like, at what point in time do the events occur? And once you know that time, you just have to evaluate those events, right? And this depends on the times that they occur, obviously depend on the randomness and also like the model itself, right? So, for example, consider a patient leaving a room and then going to speak to the secretary. So this is a type of event where the patient, so that event would be scheduled when the person enters the doctor's surgery, the doctor's room. You'd figure out how long they're there, and then you'd schedule the event for them leaving. All right. And then when they're leaving, that event's going to update the state. They're going to subtract the one from the number of people seeing the doctor, right? And maybe someone else will come see the doctor as a part of that event. But they're also going to have to add one person to the queue to see the secretary, or maybe they'll speak to the secretary directly. Right. So that event leaving the doctor's room and seeing secretary, that might actually trigger 2 more events. Right, the next person coming in and yourself in queuing for the secretary, right? And then we just advance the time to that point in time, and we look for the next event, which might be one of the newly generated events, or it might be some event that already existed. And so that's what we do. There's some nice general purpose software for dealing with these things. I haven't actually used them. I believe Anna will probably mention 1 or 2 of them. I know she's had a lot of sort of background in these kind of simulations in industry and consulting settings and so on. So let's dial things back a bit. Let's forget the doctor surgery for a minute and just do something a bit more simple, a very classic mathematical queuing problem. Okay, so just as a introduction, to build our more generic event simulator, we're going to use a very simple model, but we're going to have nice composable code which you can reuse to build more complex models. Okay, so let's consider the model where you just have a single queue. So this so-called MD1 queue. So let's think about this. The 1 means there's 1 queue. Right, that's the 1. The M stands for Markovian or memoryless. And so that first letter corresponds to how people arrive in the queue. So imagine there's a suburb and you go and there's people turning up at Coles, right? The fact that I go to Coles and my neighbor goes to Coles, they're uncorrelated, right? We're probably not getting together and collating, oh, we'll both go to Coles at the same time. We're just randomly, each of us are independently choosing to go to Coles, okay? And so when you have these kind of processes where there's all these independent events happening at a certain rate, so if you imagine like throughout the 8 hours a day, there might be 1,000 people going or something, the sort of distribution of the times people arrive are these so-called Markovian or memoryless distributions. And so for this process, it's actually one of those there's an exponential distribution for the time between arrivals. Okay, so we talked a little bit about the exponential distribution. We skipped over the Poisson distribution, which is like if you integrate that over a certain range of time, you get the Poissonian distribution. But yeah, so that's why it's sort of, you know, that's the Poisson process. Or so the M here though stands for Markovian generally. Yeah. D is D for deterministic. So once you're in the queue and you're being served, how long does it take for you to be completed? So that could be a deterministic number, like it always takes 10 minutes, for example. But you just have to wait to get to the server before your 10 minutes starts, right? And that's what MD1. And there's other queues like MM1 and MD10 and like all these different combinations you can make, and we ask questions about them. Now, MD1 and MM1 and so on, we can do some analytical solutions. So we'll talk about that. So if you consider a system like that, you might have some questions. Like if you run this over time, does the queue sort of come to some kind of semi-equilibrium where it's sort of bouncing around? Or does it sort of blow up and the queue gets longer and longer and longer and longer and longer forever? So if you imagine people arriving faster than your ability to process them, then the queue will have to get longer, right? It's just no way around that. So that's the first question. Is it stable or unstable? If it's stable, you know, describe the steady state, roughly how many people are on the queue on average, for example. How long does it take for a person to get served on average? and that kind of thing. And then sometimes you might not care about like the static distribution. You might actually care about how things evolve over time. You know, Coles is empty at 9 a.m. and then it opens and people come in and the queue gets longer and then they shut at 5, and how long does it take for that queue to drain and so on. And these are kind of like more transient behaviors. Is that a question? Yeah. Cool. So there might be other variants we want to consider here. So let's consider MM1. So remember the M was the Markovian or the Poisson distribution. So the middle letter corresponded to how long it takes to get served. Now, actually, from an analytical perspective, MM1's a bit easier to analyze than MD1, just a thing. And then there's this extension, MM1K. So the K corresponds to the capacity of the queue. So if you go to Coles and people lining up out the door, you might just turn around and go home. All right. I've done that before. So, yeah. All right. So that's the sort of thing we're going to deal with. And we're going to try and make a slightly generic simulation engine for this that can handle these different kind of cases, but with the one program. Okay, so that's what we want to do. We want to write code that can be reused to answer more questions, right? So we could code that up directly, but we're going to have a little bit of indirection here. So we have this simulator, and it's going to take a few things. It T's the maximum amount of time we're willing to wait for. So maybe 100 or 1,000 or some number. And then there's these functions. And then these constants about like what's the capacity. So that's the K in MM1K, which could be infinity or it could be some number. And how many people are initially in the queue. All right. And we got these two functions, arrival function and service function. And when we call them, they'll give us a sample of how long it takes between arrival events, drawing from some distribution. And this one will draw from a distribution for how long it takes to be served. And in the case of MD1, that's a deterministic function. It returns a constant. And in the case of MM1, that's going to be another exponential distribution, a rand of exponential of some number, right? So this is an interesting way, and we'll see this. The way you make something more generic quite often is to actually have a function which you pass functions to. All right. So remember, it's a bit meta, right? So Q simulator is a function, but some of its inputs are functions. Okay. So let's have a look at how this works. So we start at time equals 0. We start with number of people in the queue, which is init queue. And we're interested in Q integral. So the statistic we're going to care about is how many people have gone through the queue over, T equals 1,000 or T equals 10,000 or something. And that will give us an average kind of processing rate or whatever. Yeah. We want to start the system. So what were the events here? We have, what was the state? The state is just the number of people in the queue. Okay, it could be 0, in which case we're waiting for people to turn up, or it could be 1 or bigger, in which case someone's being served, and we're also waiting for more people to turn up. Right? But we don't need any more numbers to describe the state of the system. We don't care that 3 hours ago we served someone called Bob. We could forget that kind of information. We just care about how many are there right now, and that's it. And then we got some events, which is the next arrival and the next service, the next completion of service. And they're the two events, and they have times. So we have the state consists of the queue, number of people in queue, and then there are 2 types of events, which each generate the next event automatically. And for that, we just need to know when the next arrival is and when the next service is, okay? So basically, so we got the same thing before, we got this condition for when does the simulation end, right? We saw that before in the previous one. And we got okay, so we're doing an event. So the current time at the beginning of the event is sort of the new event time, but there was the event time of the previous event. We're going to use that, these two numbers in this kind of Q integral down the bottom. Okay, so we could actually have done that at the top. It doesn't really matter. Oh, no, sorry. We do that once we use these numbers at the bottom, once we know T, which is, we haven't actually yet figured out what the current event is. So if the current event's either going to be a service is completed or it's going to be someone arrives. So if next service is smaller than next arrived, that means it happens sooner. So we care about that. So this first block is when someone finishes being served. Okay. So for that, we subtract someone from the queue. Someone got served. Yay, we're done. But moreover, if there's other people in the queue, we should start serving them. And once we start serving them, we can call service function to figure out the time for how long they take to get served, and therefore predict when they get finished getting served, right? And so we get to update next service. So T equals next service, and then we get a new value for next service. Unless the queue is empty, in which case we put it to infinity, right? So it sort of never happens, right? Because this will never trigger before that loop exits, right? Because this is infinity. So that's a nice trick as well. You can use infinity and minus infinity and then and things in clever ways to make your simulation easier. The other possibility is the next event is an arrival event, in which case, well, we either start serving someone if the queue is empty, or we add them to queue, but not if the queue is too big. Okay. So if in this first block they turn up, if the queue is empty, then we predict when they'll be finished service. If the queue is not empty, we don't need to do that. But either way, if the queue is empty or not empty, we have to add the person to the queue, but only if they're going to be served, and if that's true. Now, of course, capacity is a positive number, so it doesn't really matter what order you do those two. Once we've processed an arrival event, we'll use the Poisson distribution again to draw when the next exponential distribution to predict this Poisson process to figure out when the next person's arriving. And then we integrate. So we want to find the integral of number of people in queue dt, right? And so that's your dt, your delta t. It's a discrete event simulator, so you can use deltas. And that's the number of people that were in the queue in that time range. And then at the end of the simulation, we can just divide by t to get the average number of people in the queue. So this is an interesting one. So we can do some theoretical curves for this. Like I said, the MM one's the simplest. It's just simply the queue size is like the throughput rate, the maximum throughput rate divided by 1 minus the maximum throughput rate. Sorry, the capacity of the let's go back again. Yeah, we didn't have a nice table of this, do we? So lambda represents the number of people turning up, the rate that people turn up at. Mu represents the amount of time it takes to process somebody, okay? So if this number is bigger than that number, it's not going to be stable. It's just going to explode. And then rho is the ratio of those two things. So like how close are you to capacity? If you're near 0, then you're very far from capacity. The queue's almost always empty, right? And if you're very close to 1, then you're almost operating at capacity. And what happens is this function explodes as you approach capacity, actually. You need some sort of extra leeway in your system to stop the queue getting too big, okay? And then you also get more kind of problems, more terms in this kind of formula when you complicate things, when you have a capacity limit or you have a deterministic service time or something. But we're not going to like derive those or anything, but we're just going to have formulas for those. And we're going to use Monte Carlo to estimate the answer, and we're going to compare the exact answers and the estimates, okay? So we run the Q simulator with 2 exponential distributions. Remember, this is an arrow function, an anonymous function. So this is the distribution for arrival function. When you call it, you get something drawn from that distribution. When you call that one, you get something drawn from that distribution. For MD1, we know that the service time is deterministic. It's just going to be 1 on the service rate, right? A rate is just 1 on the period. That's all it is, right? And if we have MK1, the only difference is we're specifying the K, MM1K, apologies. Yeah, we just put that number there. And so we can run this simulator and we can kind of see that, the theoretical numbers are these and the simulation results are those, and they're actually quite close. It's actually quite nice. Yeah, that's the kind of thing we're going to want to have to do with the more complicated queuing systems like you see in Project 2. Okay. So let's talk about this a little bit again. Are there any questions? Oh, here we go. We've got some questions from the time. Were service and arrival function just distributions? Oh, yeah, I did answer that. Cool. Excellent. Sorry. Is there anything kind of unclear? Am I going too fast, or is this a good speed for this kind of amount of code? Is this all right? Yeah. So one thing you might notice is the only thing we're really logging or computing is this Q integral. And therefore, when we divide it by the total time, the average number of people in the queue, right? Yeah. So that's interesting kind of thing. So why does that work? The reason that works is this system is what we call a kind of ergodic system. So in an ergodic system, ergodic's a word you use to describe Markovian processes generally, but I guess other random processes would count as ergodic. But from a technical point of view, it means from any state, you can reach any other state with some probability. It might be, so long as it's non-zero probability, it might be improbable, but it could still happen. So that means you could go from an empty queue to 10 people in the queue, right? There's some series of events that would make that happen. And you can go from 10 people in the queue to 0 people in the queue, or 20 people in the queue. Like you can get from any state to any other. You're not blocked from going from one part of the system to another, right? And so if you have a Markovian system and you have that property, then eventually there is some kind of steady state, right? Like, well, it's, yeah. For a finite system anyway. For an infinite system, the queue might blow out to infinity, but and so for an ergodic system, what happens is if you keep evolving and evolving and evolving, it will actually reach some steady state distribution, right? So at time equals 0, well, you always have that 0 people in the queue. But if you look at the distribution of queue size as a function of time, that will evolve towards the steady state distribution and it'll stay there, right? And there might be, 5 plus or minus 5 people in the queue at steady state or something like that. And there's some distribution function for that. And so what we do is we choose some large time. So remember when we ran the simulation, we set t equals 1,000,000, right? So if this simulation we ran for t equals 10, what do you think would happen? Would we get very good results? No? People are shaking their heads. So what happens is we started with an empty queue, and if we only let it go for 10 minutes or whatever, the queue size wouldn't have reached any kind of equilibrium yet, and all we'll be observing is that initial time period. But if we make time long enough, we can say that most of that 10 million units of time, it's already at kind of equilibrium. And so that when we do like the average, the queue average over the whole time period, it's sort of very close to the true average. Now, there's a bit of bias because at the beginning, there's this transient behavior where the queue's empty or nearly empty. And so the way we typically get around that is we, maybe observe the system. We try and figure out roughly how long it takes to reach equilibrium. So maybe it takes, say, 100 units of time. Okay. So what we do is we simulate for 1,000 units of time to get it to equilibrium. well and truly, and then simulate for 1 million and do the statistics over the next million, right? That, and you want that second period to be longer than the first, because that rate of going from some state to equilibrium is the same rate that you need in this ergodic distribution sense to go from one state to another, right? They're kind of related. It's got to do with the eigenvalues of stochastic matrices, but we won't get into that. Yeah. Yeah. So like, depending on what you're trying to do, you might actually use different state representations. Like you could actually represent state with every person has an identifier, like a name or like an ID number, barcode on the back of the neck. And you keep track of what every person has done. And in that way, you might want to know, like, how long is someone in the queue? Well, if you just know the number of people in queue, there's actually no way to compute that quantity. You have to actually find, you know, when did A enter the queue? When did A get served? And then add that to when did B enter the queue? When did B get served? And add that to C and D and E, and then divide by the number of people. And in that way, you can figure out how long people are in the queue for. Now, there's a sense that if you know it takes 10 minutes to serve someone, the queue's length 5 on average, then it takes 50 minutes, right? But if you want to do it, like get that distribution of things, then you can't just use a simple formula like just dividing those things. You have to actually track them and see what's going on. Right. So we've got a few minutes. What we're going to do, and I was hoping the break, we could do the break actually. We can just do it a bit early. What we're going to do after the break, and we'll break for 10 minutes, so we'll get back before 6. What we're going to do after the break is actually look at rewriting this simulator a third time. So we had sort of one version of the simulator at the start, and then we had a second one where we throw in some functions to make it more generic. And then we're going to write a third one that's more structured and more generic, and that you can use that for your project 2. I could use it for my Alara startup. You could use it to simulate atoms, like the ideal gas that I showed you. Like you do anything with it, and we'll set that up and we'll explain it and get it running. And then we might talk a little bit about the heap data structure that can make that faster and why that's necessary and how it works. Yeah, if anyone's got questions. Wait, I thought the steady state was the equilibrium. Well, I'm not sure what that means, Samantha. Maybe you can just write to me in the break, Samantha, and I'll answer. Cool. All right, have a break. We'll be back at 6:58. Yeah. Yeah.
A simulation. It's kind of wrong for something that gets in, but my expression is that we have the joint like hunter here.
Yes.
So then they get served, and then they kind of leave, whatever, and go to other place, right? Now, if we go to the queue, there should be some. We should set this kind of time it takes when we get from one queue to another, right? And if we just want to say that it is.
Oh, so we don't really have a transit time, right? Like if you're thinking of the theme park, it doesn't take time to walk from one, finishing a roller coaster to walking to the next queue. It takes 0 seconds. Yeah. I actually learned yesterday, Saturday, someone told me you can now virtually queue at Movie World. There's like an app and you're like, I want to join the queue for such and such. I've never heard of this. So it's actually a realistic model. Yeah, I know, but usually the queue's not empty. So, but yeah, no, yeah. So we're ignoring that. So obviously, there's a million ways to make these more complex and realistic.
Yeah, one issue is that, I mean, not that I'm getting back to you, so. Just trying to get a little bit of that. It's kind of a diagnosis, please. So,
So they're practical this week on this project as well?
It's just the same one as last week, so yeah, which is sort of like the intro start to project 2 anyways.
Being practical,
Yeah, it's
okay.
about similar to what's up there, right now, but
Yeah.
like using the structs to do the big problem.
Yeah, okay, good.
Yeah, they're like similar to us, and we think change the way it counts things or tracks.
Is it, are the lectures behind where they're meant to be in this course or something? No, it's not a really problem.
For reasons, projects that very different to get up.
We're not like behind according to the schedule, but I feel like we're behind according to, and maybe we haven't been pretty much the entire course.
No, as in, like the projects and tracks happen before the lectures or something.
So like just the way things are, I think.
Okay.
It's submitted like kind of like.
Yeah,
The
okay.
majority of the information you need for the project, usually the week after, just like that.
Yeah, that's true. But I mean, it might be a bit restrictive to not let you even know what the project is, maybe.
Yeah, I've got it at least.
Yeah.
Yeah, let's get into this just before this.
Yeah, I see.
Yeah, no one was gonna look at it right after.
Yeah, I see. Yeah, okay.
We had a video, but like it's basically given to us, someone's like you're really gonna get on.
Ah, yes, sorry. Yes, Samantha. So I was talking about the ergodic theorem. So if you are at a certain, I imagine maybe another way to explain it is just to bring this up, right? So let's put the lid on. There's lots of different states that these particles can be in, and if for some reason, let's say like right now the red balls are down this on this half of the screen, like how long does it take for the red balls to get over here, for example? There's some time scale between going from some state to some other state, right? Like you can obviously get to nearby states really quickly, but there might be other states which are a part of thermal equilibrium, which are in some sense they're far. It'll take a long amount of time to go from A to B. And so if you want to use the ergodic theorem and you want to actually sample all the different parts of thermal equilibrium, you have to at least wait that time scale to go from one state to a different state. Now they're both all states are part of the thermal distribution ensemble. Like all states have some finite probability of happening, but there's sort of some time scale called the autocorrelation time for like how long it takes to get from one place in the system to another, right? And if you don't, what you want to do is you want to simulate over time, which is much bigger than that autocorrelation time, so that you're averaging things which are distinct and not just average. Like if I averaged this, and I took 1 million time samples, but they're all separated by a nanosecond, right? Well, all the balls are basically frozen. You wouldn't get like a distribution. You'd almost get you'd only sample a very small fraction of the possible states. You know, I'm not sure. I hope you're listening, but not just, you know. Yeah. It's interesting because the term state's a little bit overloaded because we're using it here to describe the state of the system. But when we talk about steady state, we're actually talking about the probability distributions over those other states. Yeah, so if another way of thinking about it is going back to the trajectories. So you could argue if you just sort of look at any of these three curves, they're kind of curves that model the steady state of the system. I mean, the revenue is increasing, but it's increasing at a linear rate, right? So all three of these sort of represent kind of the steady state, but they're different, right? And so, you know, if one, let's say the green curve is a little bit below average, what's the average amount of time until the green curve becomes a little bit above average so that they cancel out? And the, yeah, I guess that's probably the best way of describing it. It's to get rid of like biases. So if I only sampled a small amount of time, like here, you know, you'd get an average rate which is smaller than it should be, which might be, you know, more like meant to be up here. But if I do the green curve for the whole way, it's not too far from the others. Over here it's good, and over here it's good. Yeah. So it's just, I was just talking about the length of time you want to simulate for, really. It just needs to be big compared to timescales of the dynamics.
With the
Yes.
with the project,
Yes.
a bit about what is it? Us to the total mean like Q length.
Yep.
Is that like for every single node you get mean Q length?
So I believe that, yeah, so yes, exactly. You get the mean Q length for every Q, and then you take the sum. Or you could do the other way around. You could keep track of the sum of everybody who's queuing everywhere in your simulator as a part of, you know, those callbacks for sampling and shit, and then divide that at the end by the number of queues. You should be able to derive it from the result that spits out. Yeah. Hey? Yeah, yeah.
Normally you just shoot, it's like 0, but like you're like lining up those numbers, for example.
No, that's exactly right. So like that previous simulation had a optional parameter for setting the initial queue size. And so you might like, what if you set the queue to 100? How long will it take to come back to equilibrium? Right? Like that's the question. Like there's lots of questions you might want to answer. Yeah. Just reminding myself. Yeah. See how much we get through. Okay. That's a 10-minute break, everyone. We're done. Okay. Does everyone know if POTS got updated recently or something? Mine won't get input and I'm getting a net error. Yeah, has anyone else had that problem? Okay. Yeah, sorry, Mitten. I don't know if you can send through some more information, but sometimes you need to like exit Julia and load it again, or call like package update again or something. So, yeah. Yeah. Okay. Taking a more structured approach. Oh, you might need yeah, okay. The worst, if it's a net error, it could be something that it's trying to connect to when you can, when it loads plots, like a library, like GTK or something. So you might want to try actually restart your whole computer and try it again. That might be worthwhile too. All right. So taking a more structured approach. Yes. So we've gone through two sort of event simulators now, and we're going to make a more structured thing. So let's just think about what were some of the commonalities we saw in these. Well, they both had, we spoke a lot about there being events and state. So that's what these two are going to represent. So at all points in the simulation, we're going to keep track of some state, some system state. Okay. And we're also going to have some set of events that each event has a time. And that's what this thing's about. Okay. And there's going to be a few more ingredients, right? At some point, the simulation ends at certain points of time where, or sometimes we're trying to extract information like statistics, like that Q integral we did, or that kind of thing. So what we're going to do is we're going to build a simulator that handles events, state, like tracking of statistics and the simulation ending, right? And what you do with it is up to you. You could build nearly anything out of it, right? And so that's the goal. And sometimes when you get the extraction right, it's actually easier for us to write this generic thing than it is to actually write a specific one. And it's easier for you to use the generic thing and program it to do what you want than it would be to write the whole thing from scratch, right? So this is the kind of sweet spot. And this is a good example of where having, not just a little dirty script to do your work, to actually have some structured programming can actually be really productive for you. Okay. So which is sort of, I suppose, the subtext of this course is about that, like doing actual real programming to solve your maths problems rather than just like a little hacky MATLAB script or something, yeah. So we're going to use a data structure called the heap, and that will turn up. So we're not going to write that ourselves. I'll talk about that later. So we import that. And as a part of that, we're going to import this function isLess. So let's have a look. We got events that happen at a time. So a timed event is a struct that has an event at a time, right? So its event is happening, and the time just notes when it's happening. And we're going to overload the inbuilt isLess function. So what is this? This probably has some kind of help. It's very much like 1's less than 2. It's very much like this. It's a little bit different in a couple very small corner cases, like let me get this right. Yes, but so when the IEEE 754 standard was released, it was always said that comparisons with NaN always returned false. Okay, so if you wanted to order things in Julia, you tend to use the isLess function to figure out if something's before the other rather than this function, because there's a few corner cases like this where it just doesn't quite work out. Another one is missing. We're going to have missing data, like missing's less than 0, missing, but isLess, missing. Here's another example where it comes up, okay? And the reason we want this is we're going to have a data structure, this heap that we keep alluding to. So there's this queue, it's called a priority queue or a heap. And that priority queue is going to need to figure out the relative priority of things, which things comes before the other. So mathematically, that's called a total order. So you have any two different things in the distribution, like they're either equal or one's bigger than the other. There's no other possibility. They can't both be greater than the other, or they can't both be less than the other. That doesn't make sense. So in Julia, the function that has that property is less. Whereas this one, it has corner cases where it's going to crash a data structure like that expects that behavior. All right. And so we're going to take bases. This is where we're doing some Julia generic programming. We're going to take base's idea of ordering, and we're going to extend that to our timed events. And then we're going to take a data structure from here, which doesn't know about our code at all, but it does know about base's idea of ordering, and it uses that. And we're going to put them together like Lego bricks, and it's just going to work. Julia will compile it all down nicely for us. We don't have to think about it. Okay, so that's the kind of productivity we want to get out of things, and that's working really well. So obviously the order, something is less if the time of one is less than the other time. Okay. Theoretically, maybe if we're worrying about NANs, we might want to use isLess on the right here as well. All right, there's going to be some structs, apologize. some sort of generic definitions going on here. So this syntax defines a function with 0 methods. So there's going to be process event. So what it's going to do is it's going to take a time, the system state, and an event, and it's going to produce. It's going to mutate state, and B, it's going to produce a list of new events. So it could be 0, 1, or 2, or 3, or 4 more events, right? So that's what this function does. And so it's there as a part of an interface that you can code to when you're doing your projects and things. There's going to be a built-in event called endSim event. So if you remember both the simulators we wrote already, they were constantly checking should the simulation end every loop, right? So this will replace that check for us. And doing it this way makes it very dynamic. You might say at the start of the simulation, I run for 100 hours, or you might want to end the event. You might be waiting for something to occur, and then when that occurs, you might end the simulation immediately. Right, so that this makes it a lot more flexible, and so we do define process event for that, and it produces some logging and an empty array of no events. Yeah. So theoretically, yeah, that's fine. And we're going to have another built-in event called log state, and what that will do. It's really just logging it to standard out, so printing out state every time this event occurs. So maybe every minute or every hour or whatever, you'll make it spit out some things. So this event, yeah, it's useful for debugging, for example. Like you run your simulation, you put these in, you kind of see what's going on. Or you could try and like collect these after the fact and do data analysis on those, but we actually have a different way of doing data analysis. So just keeping those abstractions in mind, we can actually build our generic simulator just from those. Okay, it's using the heap data type or a priority queue. I think you saw a heap sort. Did you cover heap sort when Paul was talking about different sorting ways? I think that might have come up briefly. So it's a good mechanism for, or it's probably provably optimal way of dealing with a queue where some things happen before other things, and they get inserted at arbitrary points, but you always want to get the highest priority item out. Okay, so let's have a look. This is a bit complicated. Probably the formatting's a little ugly, but let's just have a look. What we have is we have two positional arguments, init state and init timed event. Okay, so init state is the state of the system at t equals 0, right? And init timed event is the first event that you're going to run. There's a few things going on here. Let's have a look. There's max time, right? So this was going to use to create an endSim event for us. There's log times, which will be used to generate the log events for us. And there's something called callback. So we've seen a lot of functions which take functions as inputs, right? But this might be the first time you've heard the word callback. So what a callback's meant to do is it's not meant to just compute something. It's actually meant to have side effects. Okay, so callback, it's just like in your code, it's going to look like the other ones where you're just passing a function gets called. But the purpose of it is you register a callback so that you can be notified when something happens, and therefore you can do something about it. Like maybe you might write files to disk, or you might alert the user of something happening. So callbacks are used in user interface programming all the time, for example, or working with certain types of databases and things like that, right? So where you're actually having effects on the world, on people or on computers or disks or networks and different things. Like you might, for example, one classic example in networking is you make a network request. You don't know how long it's going to take for that other server to respond, right? So what you do is you register a callback function, and then it gets called whenever that comes along, right? But you're not stalling the CPU that whole time waiting. You can do other stuff while you're waiting, and then when that event occurs, that callback gets called. And that's how like all your network servers work and like your web browser works and everything. Okay, we're going to have a queue, right? And the items in the queue are timed events. So this is this binary min heap, and we'll talk in detail about binary min heap either immediately after this or the start of Tuesday's lecture. And the queue starts empty. That's the constructor obviously makes an empty queue. And we put the initial event in there, right? What else are we going to put into it? We're going to put in the end sim event at max time, right? Like I said, we could edit this to be a bit more generic, but that's what we're going to do here. And we're going to, for each of the log times, we're going to put in a log event, log state event. Okay. We're going to make a copy of the initial state. Now we're going to use deep copy just to make sure everything's completely decoupled. And we're going to set the time equals 0, right? And we call the callback, I think after every event, I believe, yeah. So we're going to call the callback at the start of the simulation and after every event. And you can use that callback to do your statistics. So that callback function is going to be given the state and the time. And so in there, you can collect whatever statistics you want from the state, because you know between the two different times, between two different calls to the callback, nothing's changed, right? That's the guarantee of an event, discrete event simulator, is that between the discrete events, everything is constant. All right. So let's look at this. Let's look at the main event loop. So when we start, we want to pop off from the queue the nearest event. We advance the time. We process the event. That event's going to mutate state. It's also going to give us a list of new events. And then for each of those events, oh, sorry. Yeah, no, that's fine. We're just going to check if it was an NSIM event. This is like a special case that's sort of built into the logic here. If it is, we end the simulation. And then for all these events that were returned, we put them in the queue. We call the callback, so which shouldn't really do anything to the simulation state. It's like, you know, if you want to record some statistics, now's a good time. And then we repeat until we get an NSIM event. Okay. So if the queue is never truly empty, because before we made it, we put in NSIM event. So we know there's at least one of those in there. So eventually we're going to get it. So we're never going to start this loop with an empty queue, right? So which is sort of a nice thing to guarantee, because that could cause errors or something. So that's a very generic simulator. So let's drive it now. Let's do something like we would in project 2. So let's look at that MD1 queue again, right? So we have mu and lambda again. So remember, this is the rate of arrivals and the rate of processing. So things are getting processed twice as quick as, no, that's 1.8, sorry, slightly faster than they are arriving. We need to create the system state. Now, remember we were talking about, I spoke about this before the break. The only thing in the state that we were keeping track in those queues was the number of things in the queue, which is an integer, okay? So it's a mutable struct, because what we're going to do is we're going to mutate the state with our events. So it needs to be a mutable kind of data structure, like an array or a mutable struct or something like that, or it might contain arrays inside it. And we're going to have 2 new types of events, and we're going to write these process event functions which tell the event simulator how to deal with them when they occur. Okay, so we have this arrival event. It doesn't have any metadata associated with it, right? In a more complicated system, you would have things inside here that tell you about where are the people arriving, what are their names, are they, you know, that kind of thing, right? Or you might end of a service events, you know, oh, what was the outcome? Was it a success or a failure? You know, this kind of thing. There might be actual data inside here, not just end. You know, if you think of the white space, it could just be like this way, but with 0 lines in the middle. But it's a bit shorter to write it that way. So let's process these events. We have some time, some state. Remember, it's actually always going to be this type of state. In fact, you could probably put Q state there. And we've got arrival event. So if an arrival event comes, what we want to do is we want to add the person to the system. This function's required to return an array of new events, right? So we should do that. And if we do that, sorry, in that array, we're going to need to have a few things in it. So mostly the time of the next arrival event. So if we think of the current time and add some time according to the exponential distribution, then this will model Poisson process. Yeah, so we create a new arrival at some future time. And if it's the only job on the server, then they can skip the queue, then go straight to the server. And so we should put an event for the server's completion. And that's going to be this deterministic time. It's an ND1 queue here, okay? So this is where, yeah, that's fine. So for example, like I said before, you might be able to keep things like mu and lambda and the kind of distribution inside these events and that kind of thing. Or, yeah. If they vary from object to object. Then finally, there's the end of service event itself, which is pretty simple. It's a lot simpler. It just removes someone from the system. And if there's someone to serve, we serve them at time 1 plus mu. So plus time plus 1 on mu. There. Okay. Otherwise, we don't have any new events. And then with all that done, the whole simulation is literally just that. Okay. Imagine we had a system with no people in it, and it starts off with an arrival at t equals 0. And we want to look at the system state at those times. We can just call that. So we've got all the logic sort of spread out like modular, so like the logic for arrivals is all here. We didn't have to care about arrivals here. It's all up there, right? And you could organize your code in a neat way where you're only thinking about one thing at a time, and the simulator will put it together like Lego bricks for you. Okay, so what we're going to do is we're going to use this callback function, which gets the state at every point in time. We're going to use that callback function to record the number of people in the queue as a function of time. We're going to create a trajectory and we're going to plot it. Okay, so we've got some globals here, which are just some arrays with time and number of things. And every time we call this callback, we're going to push something onto those arrays, right? So every time the callback gets called, we're going to push on, which means we're going to basically record every event wholesale, which, like, depending on what you're doing, you might want to subsample and things like this, right? Because it might be too much RAM. But in this case, we actually want to look, get a visual appreciation of what's going on. Here we go. We run the simulation and we put in this callback function, which is record trajectory. Okay. And with that, we've got these arrays being populated, and we can use this stitch steps thing again from before, which makes the plot look steppy instead of liney. We can plot that and we get this here. So you can see it looks like a sort of random stochastic trajectory. It's bouncing up and down, but it's never bouncing by more than one, right? Either one person enters the system or one person leaves, right? But on average, there's 5 or 10 people in the queue, plus or minus some number. Even when the queue gets very long, sometimes it gets drained all the way to empty. So you can actually see it's very interesting dynamics. It's not that boring, really. And, you know, you could imagine extending the simulation and putting like k equals 15 or something, and it wouldn't get above there. And you can do all sorts of things to change its behavior. So now, if I have all this data and I ran a long simulation, those arrays would get very big and I'd start running out of RAM. It also takes a fair bit of time to even push things to them and resize them and stuff. So it can be a lot faster and a lot more fruitful to run the simulation. This is exactly like before. The only real difference here is the callback. Okay, so we've got some globals, and globals aren't the best way to track things, by the way, but just it's a bit easier to write. Got some globals there, and what we can do with them is every time there's a callback, we're going to update these globals. So we're going to use the previous time and the current time to find the time difference. And we're going to have this integral. So we multiply the time difference by the queue size, and we update the previous time. Okay. And the previous state. Do we need? Yes, and the previous state. Yes, which we use at the next time event. Okay. And it doesn't do anything. This is a function that just returns nothing, just sort of like a void function in C or something like that, right? This is, again, a callback is something that usually returns nothing. You don't care what it does, you're just notifying it of something and it does its thing. Cool. So again, everything boils down to just a single line of code to actually run it. And here now we can put like 1,000,000 time steps instead of 100, and perform this integral. And we can see that we get a relatively good answer. It's, what is that, 1%, 2% inaccurate or something after 1,000,000 time steps. So like, obviously you could do more time steps and increase the accuracy. Okay. All right, sorry, Samantha, you've got the answer. Yeah, should we change? Yeah, okay, cool. Sweet. Are there any questions at the moment? We're pretty good. Cool. Actually, I meant to get another website open, but I didn't do it just yet. So that's pretty cool. So I'm not going to like delve more into this. You've got your pracs, you've got project 2, but just remember you can take this code and run with it. Particularly this code and the struct definitions and things up here. And you can edit it. You can change the way, you know, this works. You can change the way that works. Or you could, you know, inject your own callback. You can do a million different things, whatever you want, really, to this code to get those results you need. Remember, for example, at the very end of project 2, you're doing things like at the beginning of project 2, it's very much like this, except for there's more than one queue. So when there's more than one queue, you're going to need more than one integer there in the system state, right? But we're also asking you at the end of project 2 to do more complicated analysis, which depends on tracking how long a person waits in a queue and things like that. And so the state required to do that, even with callbacks and all the rest of the fancy stuff, you still need to keep track of individuals a bit more, right? And so you're going to have almost a completely separate system. So a system being the combination of events and state, right? That's a system. So you're going to have to basically write a second system for that. And you might keep the same events, and you might overload, for example, process events. If it's like simple state, you do simple things. If it's complex state, you do complex things, and you'd have like 2 different methods for the same kind of event, right? And if people are joining different queues, an arrival event, you know, you might want to keep track of which queues being arrived to, all that sort of thing. Or you might not. You might keep track of it some other way, but yeah. Dun, dun, dun. Anyone like to say anything? You're a quiet bunch. Okay. So at the beginning of the unit, we sort of described pretty much in depth how like that random function works. The one thing that's probably a bit mysterious, hasn't really been explained very much, is this idea of the binary heap, or also known as a priority queue. So if you remember, what we have here is this priority queue, and it gets used in two ways. There's two operations you can do on it. Oh, I think there's size. You could ask whether it's empty, right? So you could check if it's empty and then quit. That'd be something you could do. Here is popping. So take an item, find the item with the smallest time and give it to me. And you're going to mutate the heap. It's going to be removed, right? And you're going to get that event out. That's going to be returned, right? And the other thing you can do is push. So push and pop, they're kind of opposite command. If you've never heard this nomenclature before, like pushing and popping is a very common terms used in data structures and computer science and stuff. So you have a stack and you push and pop things off the stack, and there's actual CPU commands called push and pop. There's you can push and pop to a vector in Julia. So which means push would mean take a vector of some length and at the end of it, add a new element, right? And then there's a function called push first, which would add it at the start and translate everything else. And Julia can do that in a fast way without actually moving everything. It can keep track of that nice and fast. So it's something, a vector is a double-ended queue in Julia. You can push and pop from both ends and it's still fast. Okay, now with the priority queue, it's not good enough to push and pop to the ends, because sometimes you have an event at some intermediate time that you just learned about and you have to put it in the middle. And if you had a vector data structure, you'd then have to like move half the elements across by one. Okay, and so if you did that, if every time you did something, because these events coming in random, so they're going to come in random parts of the queue, right? So on average, let's say you've got to move half the elements, n. So an insertion is order n time, right? Because you have to shuffle n bits of memory around. And that's too slow. So if you have n events, all right, it's sort of, the simulation sort of becomes n squared. It sort of gets, it just slows down. What you really want is to do it much quicker. And we can actually use this priority queue, which is more like log n in the number of entries to find where to put the new thing. And we're going to use a trick. So we're going to be a bit lazy. So one thing about the heap data structure or the priority queue is that it doesn't put things in exact sorted order. It put things in a semi-sorted order. Okay. So by doing less work, we can get the same results. But when we push and pop, we get the same outcomes, but we're doing less work to achieve it because we're not trying to keep the whole list of n things sorted. In fact, the goal at any point in time is we only ever want to pop the thing on the top. Okay. So our expectation of the heap is that we can push and pop elements, and when we pop, it's quick to get the thing off the top. And it's whatever internal rearrangements we have to do is also fast. Okay. And when we push, whatever internal manipulations we have to do is fast. Okay. That's sort of the three constraints. All right. So how are we going to achieve that? Let's have a look. So the heap will let us push and pop in logarithmic time, which is pretty good, which you'll find if you do a lot of computer science, you'll see this log turn up everywhere. It's really common. So a heap is similar to a tree, a balanced binary tree. So what is a balanced binary tree? So a tree, now if we think of a tree in nature, we have the trunk at the bottom, the branches branch out and the leaves are at the top. Often in these diagrams, we draw it the other way around. So the root of the tree is this number here, and then it's tree structured after that. So for something to be tree structured, it's a directed graph where there's only ever one arrow into a node. And that makes it a tree graph. Yep. So that's tree. Binary means not only is only one thing coming in, there's at most two things coming out. That's the binary. Okay. And balanced, well, that means something very specific. So if we imagine drawing this tree, and we've written down some numbers here in binary digits, right? The first layer, you can fit a maximum of one thing in. The second layer, a maximum of 2 elements in. The third layer, a maximum of 4 elements in. The fifth, the next layer, 8 elements, 16, 32, 64, 128, 256, so on, right? Each layer gets twice as big in terms of its size. And when it's balanced, it has this property that there's only holes in the lowest layer. You don't have like something down here and like 2 levels up, something's missing. All right, so if it's balanced, it's sort of basically as flat as it could possibly imagine it being. It's never going to be, sometimes it's perfectly flat because you have the exact number of elements to fill it. But generally, no, it doesn't have to be perfectly flat or anything like that. And a lot of balanced trees, they might have a bit of fuzziness in, say, 2 levels, like an RB tree or something, or a red-black tree. But it doesn't ever, there's no like jaggedness at the bottom more than 2 levels. And so there's some sort of balancing condition. Now, why do we care about balancing? Now, imagine we had a tree where you start and you always go right, and you go right and you're right, and the left's always empty, okay? So then the depth of the tree is n, if there's n elements, and there's no branches, and that's a very, very unbalanced tree. And it doesn't have any of the nice properties. We can't do any of these kind of algorithms when it gets like that. So what we're going to do as we manipulate our heap is what we want to do is we want to put the element we care about at the top, which is the soonest thing. And we're going to manipulate everything else so that it stays balanced. And there's one more condition, which is we'll get to, which is sort of really important. But let's have a look at what we've done here. So Yoni's hand drawn these pictures, and they're beautiful. All right, we'll tell him that. So we have we're just starting with binary digits. So that's the number 1, 1, 0, that's 2, 1, 1, that's 3, and then 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So why have we done this? So I've drawn this. Well, Yoni's drawn this on paper as a bunch of different nodes, and you could imagine these arrows, these lines, if they're directed arrows, they could be. This could have a pointer to that thing, right? And they could be allocated in different parts of memory and so on. But in reality, what we often do is actually lay it out in memory sequentially, and use these numbers as a kind of index to the next thing. So rather than using the system allocator to allocate lots of little miniature objects, we'll get Julia to give us a big array, and we'll put everything in the array, and everything will point to other elements in the same array. And this is a huge optimization, right? That'll make it run 10 times faster. But that's just a factor of 10. We need to describe how the tree structure gets us what we want. So I'm not going to focus much on this array structure, but please just note, if you use datastructures.jl and you use their bin max heap, it's using an array like this underneath, okay? So it's just sort of like, rather than having some weird object graph like that, it's got an array like this. And what happens is, like, when you say, let's say you want to like swap those two, well, it's just like that, which is like a fundamental thing you do in a heap. You would just swap those two in the array, and you'd leave the rest of the array alone, for example. All right, so what we can do with this binary tree is, like, given you, let's say you start at the root node here, what we can do is either go down to the left or down to the right, right? There's some pretty fundamental ways of doing it. So we have a node object. The node knows about its parent, its left child, and its right child, okay? I'm using this union before. We've seen this union. I mean, I know I talked about it earlier in the course, but I don't know if you've really used it in anger yet. So just to remind you, a union is when something could be of type A or type B, right? So we could have parent is either a node or a nothing. So why would it be nothing? Well, the root node doesn't really have a parent, right? So we can't track it. So, you know, we want to account for all possible types of nodes. The other thing is the children are optional. You could be a leaf node. A leaf node means, remember the tree analogy, roots and leaves and all the branches in between. The leaf nodes have no children. So you might have a left child or right child, both or neither, okay? And you'd have some value associated with you. Let's say it's a string. So we're going to use these data structures that I'm about to show you to sort a bunch of strings. That's what we're going to do with it. In the next, yeah, and then that should bring the lecture to an end, I think, finishing this off, that'll be good. So we didn't really cover in this course linked lists and all these sort of computer sciencey data structures with lots of pointers and things in them, right? It's not really an intro to CS data structures course, but you should just be aware that in that kind of field, they're very ambiguous, very classic kind of data structures, right? But we'll implement using the node above, so you can kind of get a feeling for how to use recursive data structures in Julia like this. So these are very specific nodes. They can only hold strings, and the tree itself consists of some integer, which is like the number of nodes, and the root node. Now, if that number's 0, the root node will just be nothing, right? But if that number's non-zero, then the root node will be a node. Okay. So we can do, for example, a function which computes the depth of the tree. Now we know that it's one way of computing the depth is you traverse every possibility and count it up. But we actually know that this thing is balanced. So we can actually just write a function for the depth as the log base 2 with some rounding, floor and stuff. Floor is like round down to the nearest integer, never up. We can, because we know it's balanced, we kind of can find a formula for this, basically. It always obeys this sort of structure. If you cast your mind back to all the binary representations Paul was talking about with signed integers and unsigned integers and all those fancy things, it turns out you could use a function like this to make that depth function insanely fast. This is sort of, that's sort of like a constant, and this is sort of like a single processor instruction, which is extremely fast for the processor to run and pipeline and stuff. And here's a cute little function to show the tree at any point in time. So we're going to create these nice little sort of printouts like this. And I don't really want to go into this showing functionality, but basically, if you want to show a tree, you might have like a little header, which is like the number of things in the tree, and then the contents. Now, this is a pattern you see a lot, Julia, like you know, and 12. You sort of see it prints out a little header and then the contents, right? Like that. So it's sort of emulating that kind of thing. And then this thing is a way of producing a tree with pretty ASCII art, or not even ASCII art, Unicode art, using these Unicode symbols. Okay. And you have to keep track of a couple strings in order to do that. And this is not something we're going to study, really. I'll just mention it. So the most important part obviously, of this tree is pushing and popping of the heap. So the logic here is if you want to put something in the heap, you put it in the next available spot until you can't. And when you can't, you start rearranging things. Okay. So we put it there. So and pop is actually a lot simpler. Pop will actually take the element at the top because there's an invariant that the smallest thing's always at the top. And then it'll have to maybe rebalance the tree if you do that, is the only sort of caveat. But since we kind of know the layout of the tree, it's not so hard. So if we want to push onto the tree, we create a new node, which is going to have the new value. And then we're going to have to sort of manipulate the existing nodes, like change where they're pointing to and things like that. So if the tree is empty, we just stick that in as the root node. If it's not empty, we do this logic down here. We add 1 to the number of nodes. Okay. And we're going to use this binary representation. Remember these 1s and 0s. I forgot to mention the key part of this picture. It's kind of funny. The key part of this picture is, let's just start with a 1, right? Because Julia's indexes start at 1, right? That's why that's a 1. Then each time we go down, it's like a prefix. These all start with 1 and then a 0. And then these all start with 1, 0, something, 1, 0, something. And then like the children of 1, 0, 0 is 1, 0, 0, something, and so on. So like as you go down, they share the same prefix in binary. Yeah. And the one on the left is the one with the 0, and the one on the right is the one with the 1. Okay. So we don't really necessarily need to keep track even. This is these tricks that these array-based ones use. We don't really need to even keep track necessarily of these index links. We can kind of infer them directly from the binary representation of the index itself. So we kind of know that that's root, left, 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 right? And we know that this one's root, left, right, left, and that's the path to get to that element. Okay, and so that's what this thing is doing. So what we're going to do is we're going to do some bit masking. So I think this came up in big homework, I believe. One of the problems there. There's a bit of a question there about bit masking. So the number 1 is 00001 in binary, right? So it has 1 1 in it. And then we offset that by the depth of the tree. So because we were looking for the most significant bit, so we put that 1 over, we drag that 1, so it's like 001, 0000 or something, right? By the number of things, which depends on the depth of the tree. And then we use these bits to descend the tree, left or right. And while we're doing it, what we do, we want to jam the new string in here, and we have to check. Oh no, hang on, what are we doing here? Excuse me. I thought it would be manipulating it. Oh, there's the break. Yeah, sure. Num and mask. Num is number of nodes. Okay. If a bit is 1, then go to the right. That's fine. If mask is 1 and you're the last one on the right, sure. So if you're the last one on the right, okay. So it looks like in this function, when we're pushing in this heap, we're just stuffing everything at the bottom. So we're just filling everything in order. So if you imagine this array, we're just jamming them in this order as you're pushing. All right. Also, we'd be filling in that one, then that one, then that one, and then that one, that one, that one, that one, that one. Right. And then it should be. Is it not calling as less anyway? That's really weird. Oh, that's right. We haven't done this. So this is just populating a tree, but not sorting it yet. That's cool. Apologies. We will cover this a little bit again next week because we're going to make a generic version of this. So here we're just sort of descending the tree and putting elements in when we push. So it's like a simplified version of push. And in pop, we're actually doing the same descent. And I think we're just removing the last thing. So if there's only one thing in the tree, we need to set the root to nothing rather than a node and get the value. And if there's things in the tree, we need to do the same move left, move right sort of pattern. And once we get to the thing we're interested in, which is the last one, then we can do that here, which is just sort of manipulating the children of this root, of this thing. So node replaced with root. Yeah. Get this right again. Sorry. This one's confused me. It's thrown me. If you're not the last one on the right, you descend. If you are the last one on the right, node replaced with root equals current node dot right child. Okay. Current node dot right child is nothing. The thing you're replacing with root is parent is nothing because it's the root. You put them in. That's interesting. So it's sort of flipping it around as it pushes it. So let's have a look at how it does it. We put in these numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can sort of see one sits at the root of this tree. And the other one's sort of populating in the order I said. 2 goes and 3 go on the next layer, and then 4, 5, 6, 7 go on that layer. And then the leftovers make the final layer. They don't complete the layer, but they're sort of biased over to this side. And so our binary heap is always going to have this shape at all points. And what we're going to do is we're going to enrich this push and pop thing so that as we're putting things in, we're actually going to flip things around a little bit as they go. And they're going to end up in the order so that the smallest thing, in alphabetical order in this case, goes at the top. Okay? So if we, for example, we take this tree and we want to pop it, again, it's just literally taking the last thing we put in, because we haven't done any of the sorting stuff yet. This is a very simple data structure where we're just like populating the balanced binary tree, but there's no other extra property. And so we're going to enrich this with another nice property for the heap. So that was just a tree which maintains the balanced property, but didn't really have any relationship between the nodes. That's what got me thrown. I thought we were jumping straight into the heap. And so these algorithms just put things, find the place to put things in order, right? What we're going to do in this max heap is we're going to, as we put things in, we're going to flip them around so they're in some special ordering. And it's going to have a certain invariant. And the invariant is quite easy to understand. It's that a node is always smaller, or if it's a min heap, it's always smaller than its children. If it's a max heap, then it's always larger than its children. Okay. And if it's a max heap, that means the largest things at the top. And if it's a min heap, that means the smallest things at the top. Because from the root node, as you go down, you have everything, right? So if, let's say, every node is smaller, has a value that's smaller than its children, all right? And then the grandchildren, the children of the children, they're going to be smaller again. And the children of the children of the children, they're going to be smaller again. And so by transitivity, the root node will have to be the smallest element. Otherwise, so if you just, what we're going to do is as we insert things, what we're going to do is we've got this place we want to put it, right? But if ever we encounter something smaller than, something bigger than us, let's say you're at the root node, right? You encounter the root node and it's bigger than me. Well, I want to be the root node now. So I put myself there and I push everything else down. and we push it in the direction that we were originally going to go. So this path these paths that we were taking in these loops here, they're deterministic. They're just determined by the number of things in the queue currently. But the swapping that we do depends. Eventually, we get to the point where we start. Oh, I'm going to be here, and I've got to swap everyone down. Okay. And so this idea of swapping everything up and down is sometimes called sifting. So we can sift up and we can sift down. And that's basically taking two nodes and exchanging values, right? So you might exchange something with the left child or something with the right child or something like that. So let's start with the simplest one, which is sift up. I'll try and cover this working and then end today, and we'll cover it again because it'll be a bit quick. I just don't want to kind of like leave you completely hanging. So sifting up means if the child is, so we push a new element to the heap, but we're going to shift everything as we go around. So it's sort of like twisting it. It's sort of, and when we push things on, we put it in place. Where's the comparison? Oh, here's the comparison. Yeah, sorry. So we start at the plate thing that we put in, and we ask, are we bigger than or smaller than the parent, right? And this is a max heap. So we ask if we're bigger than the parent. If we are, we want to swap with them, and that's the sift operation. That's just reversing the direction of these pointers, essentially. And if we want to push, so we put it at the bottom, and then we try and look, are we bigger than the parent? If we are, put me there. Am I bigger than the grandparent? If I are, put them there. And that's what this while loop is. Is it a while loop? Oh yeah, here, not a while loop. It's a recursive function call. Apologies. Not a while loop, which again, it just calls itself. So it repeats until this is no longer true. And so you're in the right place. When that stops being true, your parent is bigger than you, or you're the root node. And that's when you can stop. And then there's, this is the logic for shifting down. I'll cover that next week because I'm halfway through and it's 6:50. But it does the same thing. When you pop the thing off the top, we're going to have to promote something to be there, and we're going to have to like bubble up things into the holes. So we're going to actually follow a downwards trajectory to kind of bubble things up, make it balanced again. And what we can do is we can put in a bunch of strings, like here's some prime ministers. We've actually got more since the last time this was written, which isn't surprising these days. And we can put them in this heap and they'll come out in an order. So this was a max heap. So that means in alphabetical order, the last thing, the biggest thing is the end of the dictionary. And then we can put them all in and then pop them all out, and we get them in reverse alphabetical order. Yeah, so I'll recap this, especially this, on tomorrow, just tomorrow, and we're going to go through it again and figure out how to make a modular max heap. So we're going to make like data structures.jl, how they export one. How would you go about creating one of those and using them in your code? Now, it's not necessarily that you really absolutely must do it this way for your project too, but it does sort of begin to make it possible to do it this way if you want to do it. And so it's just good practice for, writing reusable code. And I think, for me, that's what I'd love for you guys to get out of this, is that you can write code you can share with other people and reuse, and is correct and things like that and fast. So. All right, hang on, the chat has a couple of things. Oh, sorry, Matan. I'll write to you, Matan, now. All right, thanks all. Okay, so as I sort of maybe alluded to, but maybe you missed, when you put things in the tree, there's sort of a determined spot which will get pushed to. Bye. So it doesn't matter which things are bigger or smaller. That new slot is going to get filled by something, right? If it's a max heap, it's going to be filled with something relatively small. If it's a min heap, it's going to be filled with something relatively big. And the opposite happens when you pop. There's going to be a slot which is preordained to be empty at the end of the operation. All right. And what you do is you take the thing off the top, which is going to be the biggest, the smallest, and then you're going to work your way down to this spot that's meant to be empty. And it's like playing that little game they have as kids where you push around the blocks, but there's like almost a full grid, but there's one empty square, and you're kind of like moving around the hole. And so you kind of like play that game where you move that hole down to the bottom. The hole starts at the top, but there's this preordained square that needs to be empty, and you work your way there. Either just simply flipping things up or dragging things away in a more complicated way, which so the height of the tree is exactly given by the depth function. So if you remember, we had a depth function. Because we know exactly where things go, this depth function we have there is always the depth. So before or after every proportion pop, this relationship's always true. And the pattern we always use is exactly like here. It's sort of like we're filling up one layer at a time, going left to right, always. Or if we're removing elements, like if we're going to remove an element for this tree, we're always going to remove that element. Well, that element's always going to be either popped off or it's going to, I'll have to probably move here in this case, right? Because you'd pop off the thing on the top and there'd be a hole there and you'd need to get here, so you'd swap it with him, okay? After you swap it with him, you need to check whether it's bigger or smaller than him. You might need to swap with him too. And then you work your way down here until the hole's here. And you have this new perfectly balanced tree. And there's always log n steps to get down. So that's always a log n operation. So yes. Hey.
Just got a couple of questions about the assignment.
Yeah.
It's just like
Maybe I'll
general.
turn off.